Yeah, today I'm going to talk about recent work on catalytic entanglement uh, with Borun and Alex. So here we mainly focused on state transformation under catalytic LOCC. You can find this work on arXiv. And if you have any questions or comments during the seminar, please feel free to stop me. So here is the overview of my today's talk. First, I will give a brief introduction about state transformation in single copy and in asymptotic limit, and then some previous works on state transformation using a catalyst. Then I'll go into discuss about our work on catalytic LOCC transformation, and then I'll provide two application of that on quantum state merging and on assisted entanglement distillation, and then finally I'll conclude. Okay, so yeah, so in resource theory of entanglement, we are mostly interested in the state transformation under local operation and classical communication. To be precise, one can ask that following question, like what are the states we can achieve from a given resource state rho under LOCC? So one of the pioneering results in this direction was provided by Nielsen. Actually, Nielsen classified the possible transitions between pure states in terms of the square of Smith coefficients. In fact, the transition from psi to phi is possible if and only if the following relations are satisfied for all k, where these lambda j are the Smith coefficients in descending order. Now this relation states that phi majorizes psi. Now, in another way, we can say that the transition from psi to phi is possible when the subsystems of psi are more mixed than the subsystems of phi. However, this criteria provides a partial order, as the reversible conversation among psi and phi is only possible when the square of the Smith coefficient of both the states are equal. And also there exist many other such states where the interconversion is not possible. So generically, under LOCC, the pure state transformation is not reversible. However, this reversibility, we can lift this reversibility by taking many copies of the system. So in the asymptotic limit, or in this region, we are mainly interested in the following protocol. Like given n copies of a state rho, we achieve a joint state sigma m by applying a LOCC operation on the big state rho tensor n. Now, if for some large n, if this joint state sigma m is arbitrarily close to sigma tensor m, which we can quantify via trace distance and which vanishes in the large limit, then rho can be transformed into a state sigma with rate m over m. Now this rate, for pure state, this rate can be quantified via von Neumann entropy of the subsystems. Now for bipartite pure states, the entanglement is usually quantified via the entanglement entropy of the state, which can be defined as this, like the von Neumann entropy of the subsystems. Now this entanglement entropy and entanglement distillation are very closely related. However, the connection between this entanglement entropy and entanglement distillation, the relation we only know in the asymptotic limit. And the concept of entanglement entropy in the single copy region is so far remained open. So here in this work, we actually succeed to close this gap by using catalytic LOCC transformation. So So actually the concept of catalyst was originally introduced in chemistry, where some chemical reactions, where we can increase the rate of some chemical reactions by introducing a catalyst. Such that the catalyst is not consumed in the process and we can reuse it without any extra cost. Similarly, in quantum catalyst is like a quantum system which we can use it in a process where such that it will remain same in that process, and we can access to those transformations which are not possible without it. So one of the first results in this direction was given by Jonathan and Plenio. In this work, they considered two bipartite pure states like psi and phi, which we cannot go from psi to phi using a LOCC. However, this transformation is still possible if we consider an additional entangled system as a catalyst. Like we take the system psi tensor tau and operate a LOCC operation on that, and we can achieve phi tensor tau. Note that the state of the catalyst remains unchanged, and so that we can reuse it again and in some other process. So, but after this result, the power of catalyst has been explored for different scenarios, like for pure states, mixed states, multiple copies, some other results also there. However, a complete characterization of pure state transformation with a catalyst is so far remained open. And not only in entanglement theory, catalysis is also useful in some other resource theories. Like in quantum thermodynamics, recently it has been used to lift the well-known second law in classical domain to many second laws in quantum domain. Also, it has been shown that it is useful in resource theory of purity, resource theory of coherence, resource theory of asymmetry, many and many more. Okay, so here is the pictorial depiction of our catalytic LOCC transformation. So we are interested to transform a system which is in a state rho s, and we would like to transform the state to sigma, very close to sigma s. So like we take a catalyst in state tau NC, and jointly we apply a catalytic LOCC on system and catalyst, and in the final state we get back our system very close to sigma s, and we get back exactly the catalyst. So the process can be represented like this, where if we trace out the catalyst, then we get back the system in the final state. And we demand that the catalyst remains unchanged for every n. Like if we, in the final state, if we trace out the system part, we will get back the catalyst exactly. And also the system decouples from the catalyst in large limit. Like to be precise, we demand that the trace distance between the final state, which is like mu n SC, which we get by operating a lambda n on the joint state rho s and catalyst. This is arbitrarily close to a product state of this form, which can be quantified by this trace distance. So these are the two constraints we demand in our protocol, such that this catalyst can be reused again. So equipped with these properties, we can state the following theorem. If rho s can be transformed into sigma s via asymptotic LOCC with unit rate, then there exists a catalytic LOCC protocol transforming rho s into sigma s. So I will not go very details in the proof, but I'll just briefly explain how this protocol works by this picture. So here is we would like to transform the state rho to state sigma using a catalyst. So the catalyst is like a acting on the Hilbert space of n-1 copies, and there is an auxiliary system which is only with Alice. This serves as a registrar. So the catalyst, we can prepare this catalyst like this way. Like we take a big system, sigma, n-1 copies of sigma, and then in the next one, we trace out one part and put one row there. In the next step, we trace out two parts and put two rows there. In this way, we go up to n. So the catalyst is like this equal mixture of all these states. So this is like a mixed state, big mixed state, this catalyst. Now the catalyst was actually explained in this Duan paper. After that, this catalyst has been used very recently in these two papers. These two papers are basically on quantum thermodynamics, where they have shown the advantage of catalyst in some state transformation. So now the protocol, so the protocol works like this. First, Alice will measure on our auxiliary systems and communicates the outcome to all other parties. By the way, this theorem is applicable for any multipartite LOCC protocol. So now this, if Alice gets the outcome in, then all the parties perform a LOCC operation on this system and catalyst together. And for other outcomes, they do nothing. So now, yeah, so for when the outcome is n, they perform a LOCC operation on the n copies of rho. So in the asymptotic limit, we know the result that if we perform a LOCC operation on this big state rho tensor n, we will get something sigma n. So after this process, the Alice will relabels her register via a unitary such that this n will be relabeled by 1 and I will be relabeled by I plus 1. Hence, if we relabeled the register of n by 1, then this state will be here with 1 register, and subsequently this will go one step down like this. Now in the next step, all the parties will apply a swap unitary in their system, like the system n will go to system 1 and system I will go to system I plus 1. So what will happen if we apply the swap unitary? So we'll take one sigma from here, we'll put here. Here we'll put one sigma from here, put here, and then this row will go inside, and this sigma will go here, and there will be this catalyst will be all in row. So you can see we get back in the final state, we get one sigma from row, and we exactly get back the catalyst, which we can reuse again. So this is the catalytic LOCC protocol. Now using this protocol, we can show that we can go from rho s to sigma s, and the catalyst exactly decouples in the limit. Okay. Okay, so now I'll move to this catalytic LOCC and squashed entanglement, where I will show that in bipartite case, this squashed entanglement is a monotone under catalytic LOCC. So for bipartite states rho AB, the squashed entanglement is defined as taking the infimum over this quantum mutual information over all the extension of rho AB, where this I is the quantum mutual conditional quantum mutual information of the state rho AB. Now, this actually this was introduced. This squashed entanglement it was introduced in this paper, and then there they showed that this squashed entanglement satisfy these properties, like it is an entanglement monotone, it is super additive in general, and also additive on tensor products. So what does that mean? This super additivity means this one, and if we have like if the states are like products, then we can have the equality here. And also the continuity of squashed entanglement is proved in this paper by Alice and Fanis. Now, using these properties, we can prove the following theorem. Like if a bipartite state rho AB can be transformed into the state sigma AB via catalytic LOCC, then the squashed entanglement of rho AB is always greater than equals to squashed entanglement of sigma AB. Now the proof is so the proof is very simple. Like so the squashed entanglement of the initial system and catalyst should be greater than equals to squashed entanglement of this state, actually mu and SC, where we use the property monotonicity property of squashed entanglement. And as squashed entanglement is continuous, then the squashed entanglement of this state is very close to the squashed entanglement of this product state sigma S and tau in C. So we can write the squashed entanglement of initial state must be greater than equals to squashed entanglement of the final states. And now as the squashed entanglement is additive, we can write that squashed entanglement of the initial state should be greater than equals to squashed entanglement of the final state. So in this way, we can prove the if and only if condition, like rho AB can be transformed into sigma AB if the squashed entanglement is always greater than equals to the squashed entanglement of the final state. Okay, so now moving to the bipartite pure state scenario. So for a bipartite pure state,
Chandan,
yeah.
Can I interrupt you?
Yes, yeah, sure.
So why did you actually here focus on squashed entanglement, and what about other measures? So for other measures, it doesn't work, yes?
Yeah, so just to prove that we need this additive thing and the continuity thing to prove it. If some measures satisfy these properties, then we can also use that.
Yeah, but if I could add something, I mean, basically, we don't know any other measures that fulfill properties B. This super additivity, it needs to be super additive and additive on the tensor products. So I don't know any other measure that fulfills these two.
I mean, but what, distillable entanglement doesn't satisfy this?
It's conjectured to be, I mean, do you know this strong super additivity? I mean, it's conjectured that you can put two bound entangled states tensorize them together and get a distillable state. So it's not additive on the tensor product. Then I mean,
no, but it would be super additive, yes.
Yeah, but it additionally needs to be additive if you have you see.
Okay, with equality. Okay, with equality for this. Okay, this I missed. Okay, now I see. Okay.
Yeah, the inequality is satisfied for distillable entanglement. Yes. You're right.
Mm-hmm. Okay, now I see.
Okay. Yeah, so like for bipartite pure state, psi AB, the squashed entanglement is equal to the entanglement entropy. So now if we combine these two theorems 1 and 2, we can state the following, like Alice and Bob can convert psi AB into phi AB via catalytic LOCC if and only if the entanglement entropy of psi AB is always greater than the entanglement entropy of phi AB. So you can see we can provide an operational interpretation of the entanglement entropy in the single copy scenario, which was missing so far. Okay, so this is our main result on catalytic LOCC transformation. Now I will give.
So Chandan, can I interrupt you again?
Yeah.
Because okay, it looks very interesting because I mean typically standard entropies refer to asymptotic scenarios, yes?
Yes.
And here you claim to have some corollary regarding single copy, which involves standard entropy measure.
Yeah.
Okay. So do you think that you could use also this Rényi entropy here or something like this? I don't know. Because it's strange that actually a von Neumann entropy should be some distinguished measure here, no? If it's not asymptotic. Statement.
Yeah, I don't know about Rényi entropy, whether it will be applicable.
I mean, if I might add something, I mean, this corollary that is shown here, it's if and only if. So the von Neumann entropy completely characterizes state transformation. So I don't think that other entropies are relevant here. The catch is that, although, as you said, it's about single copy transitions, the catch is that we need a catalyst that diverges. So the demand to get the transition
yes, no, I see. Because catalyst involve also psi and phi states.
Well, yes. Yeah, but it's not. I mean, this is not a problem because in the idea of a catalyst that you can adjust, that you are free to use any catalyst for a given.
Yeah, I see. But now I understand because there's like many copies of psi and phi in the catalyst. So that's why somehow this standard entropy appears, because there is basically like infinite copies of state in the end.
I mean, for me, it's more because you have a divergent catalyst. So we can actually, this is not, I think Chandan is not presenting it, but we can actually prove that you need a divergent catalyst in some cases. I mean, you cannot do it with a finite dimensional catalyst.
Okay. Now I think I see. Okay, thanks.
Okay, so now I'll move to this application part so I'll first start with the state marching thing. So basically this quantum state marching was introduced by Hordejke, Oppenheim and Winter. So in quantum state marching, we assume that there are three parties like Alice, Bob and referee share a state, many copies of a state psi RAB. And the aim of this Alice and Bob aim to transfer the state of Alice to Bob via some LOCC operation, such that the final state psi RBP tilde is very close to psi RAB, with up to a relabeling of this A and B tilde, and the correlation is preserved. So there are like these three possibilities. Like if the conditional entropy is 0, then there exists a LOCC protocol which take the state psi RAB tensor n to epsilon close to the state psi RBP tilde. Now, if this conditional entropy is greater than 0, then we need to provide additional n copies of entangled states shared between Alice and Bob with same entanglement entropy as H psi A condition P. Now, in this case, if we apply a LOCC operation on this joint state, then in the final state we can get to this final state epsilon close to this final psi RBP tilde. However, if this conditional entropy is less than 0, then by applying a LOCC operation in the final state, in addition, we can get back n copies of entangled states shared between Alice and Bob with entanglement entropy minus of this conditional entropy. Now, we would like to perform this thing using our catalytic LOCC protocol in single copy. So to do that, we have the similar protocol, like there is a Alice, Bob, and referee sharing a state psi RAB, and additionally they also have access to a catalyst in state tau n. Now, in Alice and Bob will perform some LOCC operation jointly on this catalyst and on their respective systems. And in addition, the referee needs to perform a local operation, which is independent of what Alice and Bob are doing. So if we do this if we transfer using this catalytic state merging, then we can check that this can be transformed, this initial state can be transformed to epsilon close to psi RBB tilde with the catalyst remains intact. In fact, we can prove the following theorem, where if rho RAB can be converted into sigma RAB via asymptotic LOCC between Alice and Bob with unit rate, then rho RAB can be converted into sigma RAB by applying catalytic LOCC between Alice and Bob and a unitary on referee side. But note that this unitary is independent of what Alice and Bob are performing on their system. So actually this theorem is more powerful because this states that for any state rho, we can convert into a sigma, but we just need two pure states here. So theorem 3 states that catalytic state merging is possible when this conditional entropy is less than 0. And additionally, Alice and Bob can obtain an entangled state with entanglements with same entanglement entropy as like minus of this conditional entropy. Now in the next slide, I will prove this optimality that one can obtain at most this much of entanglement entropy by performing a catalytic LOCC protocol. In other cases, when this conditional entropy is greater than equals to 0, this catalytic state merging is possible when Alice and Bob are provided with, we need to provide an additional entangled state between Alice and Bob with at least entanglement entropy is equals to same as H psi A condition B. So in the next slide, I will show that we need a minimum this much amount of entanglement entropy to have this kind of catalytic LOCC protocol when this conditional entropy is greater than equals to 0. Now, actually, we can prove this, prove the optimality using the properties of squashed entanglement. So first, the optimality when we have like H psi A condition B is less than 0, we can additionally get back some entangled system between Alice and Bob. So I'll prove by this via contradiction. Like let's consider there exists a LOCC protocol such that the squashed entanglement of the system phi 2 A prime B prime is more than minus of this conditional entropy. Now let's consider this bipartition between Bob and Alice and referee for the initial state psi RAB. So you can see that if we consider this bipartition, then the quast entanglement of this bipartition is just the von Neumann entropy of the subsystem psi B. Now in the final state, when we have like an additional entangled state between Alice and Bob, then the squashed entanglement of the final state is nothing but just the von Neumann entropy of psi this partial state psi AB and the additional entanglement from the state phi 2. Now you can, if we use this, if as we have assumed that this is greater than this, then the squashed entanglement of the final state we can show that is greater than H von Neumann entropy of psi b, which is actually the squashed entanglement of the initial state. But as we prove in theorem 2 that the under catalytic LOCC squashed entanglement is monotonous. So there is a contradiction. So this is not possible, and at most we can have a entangled state with entanglement entropy exactly equals to this minus of this conditional entropy. Now for the other case, when this conditional entropy is greater than equals to 0, again we can consider the same cart, like we have a initial state psi RAB and we need to provide an additional entangled state between Alice and Bob. Then we can perform, if we check the squashed entanglement in this cart between Bob and Alice and referee, then we can see that this is nothing but just the von Neumann entropy of Bob state and this additional entanglement shared between Alice and Bob. And if we just consider the squashed entanglement of final state, this will be just the von Neumann entropy of the initial state psi AB. So you can see that this is the squashed entanglement of the initial state is as by monotonicity. Squashed entanglement of the initial state should be greater than equals to squashed entanglement of the final state. So entanglement entropy of phi 1 should be always greater than equals to this conditional entropy. So it says that we need to provide this much of amount of entanglement to perform this catalytic LOCC operation. But note that this is powerful in the sense that here we need like n copies of the system, and then we perform a LOCC operation to merge the system on Bob's side. But here we can do it with a single copy and a local. We just need to perform a local operation on the referee side. So this is one application. The next application is on assisted entanglement distillation. Here, let's consider Alice, Bob, and Charlie share a pure state psi ABC. Now, by performing catalytic LOCC among all the parties, they aim to convert the state to phi AB, which has maximum possible entanglement entropy. So there are like two cases here, like the conditional entropy between Charlie and Alice, which is nothing but like this von Neumann entropy of the reduced state psi AC, and the von Neumann minus the von Neumann entropy of the reduced state psi A. Now this psi AC is von Neumann entropy of this state is nothing but the von Neumann entropy of psi B. And if we take that this is less than 0, then Charlie needs to merge his system with Alice using a catalytic LOCC. And as a result, Alice on Bob will end up with a state having entanglement entropy H psi P. Now in the other case, when H psi C condition B is less than equals to 0, then Charlie needs to merge his system with Bob. And as a result, they will get back this state phi AB with entanglement entropy H psi A. Now, in this catalytic assisted entanglement distillation protocol, we can get phi AB from psi ABC with entanglement entropy is either equals to minimum of either this H psi A or minimum of H psi B. In fact, we can prove the converse also, like if we can get back an entangled state phi AB, which is upper bounded by this minimum of this von Neumann entropies. So to prove that, we can again use the properties of squashed entanglement. We know that any tripartite LOCC protocol is also bipartite with respect to any bipartition. Then if we consider this case, and if we consider a bipartition between A and BC, then the squashed entanglement of the initial state is nothing but the squashed entanglement of is nothing but the von Neumann entropy of H psi A. This is equals to, and as squashed entanglement is monotonic under catalytic LOCC, this should be greater than equals to squashed entanglement of the final state. And similarly, for this case, the squashed entanglement between bipartition B and AC is nothing but the this von Neumann entropy of the reduced state psi P. And as squashed entanglement is again monotonic, so this H psi B must be greater than equals to the squashed entanglement of the final state. So it means that in this catalytic LOCC protocol, we can convert psi ABC to phi AB, where the entanglement entropy of phi AB is upper bounded by minimum of these von Neumann entropies. Okay, so this is another protocol where we can use this catalytic LOCC transformation. Okay, so now I'll just conclude. So this catalyst offers a significant enhancement for entangled state transformation, such that previously we know results in the asymptotic limits only, but that we can translate into single copy scenario also. The advantage of catalyst has been explicitly shown for bipartite pure state transitions in quantum state merging and in assisted entanglement distillation. We can assume that the similar results will also hold for other quantum information protocols. For example, see recent result on catalytic quantum teleportation. And furthermore, using recent results on multipartite scenario, we believe that this technique could be extended to the case of multipartite state transformations. And we believe that this similar approach might be applied to other resource theories like thermal operation, purity, asymmetry, and stabilizer computation also. And thank you. That's all.
Yeah, thanks, Chandan. Okay, are there any questions? Rafa, you don't have questions?
So, okay. No, I'm just wondering if I could think of some use of catalyst in quantum metrology, but I don't know.
Can one do LOCC in metrology, local?
I mean, okay, in principle, you have these models of distributed sensing. So where you have, different sensors in different locations. And then in principle, you can restrict class of, I don't know, measurements or something to be something like LOCC. So maybe in such scenarios, you could think of something similar.
Mm-hmm. Yeah, I'm not sure. You would need to define some concepts, some transformations that kind of do not increase the usefulness of a state for metrology, and then that. But yeah, maybe Chandan has thought about that. Question for Chandan.
I have no idea.
No, so in general, I like this result that somehow you have this like single shot statements which are like, okay, where this asymptotics is somehow hidden in this catalyst in some sense. Then yeah, okay, it's I think it's nice.
And related to your question to this other Renyi entropies, it might be that if one goes if one tries to refine it somehow, let's say if you want, I mean, in our case, to reach optimal transformations, you need a divergent catalyst, right? But if you try somehow to bound the catalyst somehow, or to bound how it maybe if you try to put some boundaries on the way how it diverges, then you might get again like a richer structure with more entropies that characterize it. Maybe something like that.
Yeah. Okay.
Well, you know, it's somehow, yeah. So I think overall, what one can say is that if you like this von Neumann entropy completely characterizes transitions if you allow a catalyst to be correlated with the system, but in the limit of a large catalyst, these correlations go to zero. So in the sense, this catalyst is truly a catalyst in the limit. No, that because it becomes completely decoupled in the limit, or you can push the correlations between the system and the catalyst to below an arbitrary small threshold. No, and then it becomes like truly catalytic. In the limit of a very large catalyst, yeah, which then can be truly, I mean, reused in a sense, no, in a catalytic way.
Yeah. Okay.
And no more questions from the audience. Don't see any. Okay, then let's. I guess we close here and. Then yeah, see you next week, right, Rafał? Next week.
Yes. Thanks.
Okay.
Thanks and see you. Bye bye.
Thank you. Bye.